Susie, and this is the one about optimising when there's more than one maximum or minimum point. So here's a maximum and minimum point, also known as stationary points and turning points. What's really important here, and what's important for the plot of this video, is that at these points the gradient is exactly 0. If you imagine a tangent line just at those very points, then it is going to be a horizontal line, and a horizontal line has a gradient of 0 because there is no change in y divided by the change of x. Change in y is 0, so the gradient is 0. So we know that the maximum and minimum points are where the gradient is 0. So we can find where those points are. And here's the 3 steps. We differentiate to find the gradient or the marginal change function. We set that equal to 0 because we're interested in the point where the gradient is 0. And then we solve for q. We say, oh, tell me, mighty calculus, the value of q that gives a gradient of 0, because those are our elusive maximum and minimum points. So here's a function. Let's see if we can find the maximum and minimum points. So we need to differentiate first of all. dr by dq is going to be, and I need to multiply the power by the coefficient and drop the power by 1 plus 2. And because we're interested in where this gradient function is equal to 0, we set it equal to 0. And then we notice, oh, it's a quadratic. It's a quadratic because there's more than one solution. In this case, there's 2 solutions. So any quadratic can be expressed in this form. So let's just think about that in this form, and it's sort of in the right order, isn't it? So we can read and say that a equals 6, b equals -8, c equals 2. Now, we can either substitute this into the quadratic formula, or we can use a calculator. I'm going to use an online calculator, actually. So I'm going to use the maths.com online one, which I've used in a previous video. It's a really good site, but there's lots of sites that will do this for you. But you'll notice they all want you to put the coefficients in a particular order. So here's us online, putting in these values, 6 minus 8, and c is 2. And then I press solve, and then my solutions come up. So it turns out then that there's maximum minimums at 2 points, where q, let's call this q, equals 1 and q equals 0.33. So we've found our 2 points, but, and it's a big but, how do we know if the points that we found are maximum or minimums? Well, here's the function we were looking at before. So how do we find if maximum minimums? Well, fortunately, it's easy. We find the second derivative. And the second derivative is where we take the first derivative and differentiate it again. And that's the symbol for that. You sort of dot a few 2's over there. So let's have a look at this. So here's the first derivative, like we did on the previous screen. And the second derivative is where we just differentiate that one. So we get 12q minus 8. So we found the second derivative. Pretty fancy, huh? And what do we do with that? Well, we then substitute in the 2q values that we found, one at a time, and then do the following test. And here's the test. If the second derivative is positive, i.e. if it's greater than 0 after we've substituted in one of the values of q, then we know it's a minimum. It's like that. It's a minimum point. Whereas if it's negative, the second derivative is negative, it's a maximum. And this is how I remember. Positive people are smiley people, and they smile like that. They smile like a minimum function, whereas negative people are frowny people, and they frown, and that looks like a maximum. All right, so back to this one again. This is where we got to. We found the second derivative. We solved for that. We solved for this, didn't we? We put in our 6, our minus 8, and our 2, and we got those 2 answers. So now the big question is one of those a maximum and one of those a minimum? Well, let's see. In order to find that out, we've got to find the second derivative. So I'm just differentiating the first derivative, and I get that. So when q is equal to 1, the second derivative, oops, that's R. The second derivative is equal to, substitute in 1 there, I get 12 minus 8, which is a plus 4. And it's a positive number, so positive people are smiley people, so it's a minimum. But when q is equal to 0.33, the second derivative is 12 times 0.33. That's really a third, so that's going to be 4 minus 8 is minus 4, and that's a negative number, and negative people are frowny people. So it's a maximum. So let's do a second one. Make sure that wasn't a fluke. So we've got a cost function, a nonsensical cost function. Let's differentiate it because we want to find the stationary points and find again if they're maximum minimum points. So here's us differentiating dq. So 3 times a third is 1. So it's just q squared. We don't bother to write 1. Minus 4q minus 8. So there's our derivative. So we're interested in the points where the derivative is equal to 0, because that's where the maximum minimum points are. So here's us setting that equal to 0 and recognising again that it's a quadratic. So we're this time round, a, the coefficient of q squared is 1, b is minus 4, c is minus 8. Then we get back our handy dandy calculator. We write in our a, b, c values. We press solve, and we get 2 values of q that solve this quadratic. So these are the 2 values of q where we have a maximum and a minimum. But again, we want to know whether each is a maximum or a minimum. So what do? We have to find the second derivative, which means differentiating the first derivative, and it's 2q minus 4. I'm going to need a calculator for this. Alright, so when q is 5.46, the second derivative is equal to 2 times 5.46 minus 4. In actual fact, we're not really interested in the size of it. We're only interested if it's positive or negative. So we could tell that was going to be a positive number. So that's a positive number. Positive people are smiley people, so we know that one's a minimum. So that one's probably a maximum, but let's just check. When q equals minus 146, the second derivative is 2 times minus 146 minus 4, minus 6.92. Oh, I guess it's the... So it's a negative number. It looks like it's the negative version of that. It's a negative number, and negative people are frowny people, so this one is a max. So, 2 big stories of differentiation. One is by differentiating we can find the marginal change function, or the gradient function, and find the marginal change at any value of q in that function. That's pretty good. But we can also set that marginal function equal to 0, and if we solve for q, we will find the points of maximum minimum of that function. Wow! Okay, just a couple of points about what we've been doing really, and putting it into sort of mathematical economic language. So if we want to prove that a function reaches its maximum at a particular point, we have to look at the first order condition. The first order condition is where the first derivative must be equal to 0. It's what we call a necessary but not sufficient condition. To be a maximum, the second order condition must also apply, and the second order condition means that the second derivative must be negative. So if those two are true, then we've proven we've got a maximum. And we've got a minimum if the second order condition shows that the second derivative is positive. So, by the way, we've been looking at second derivatives. Let's just finish on this one. There's also a third derivative. Actually, there's an infinite number of derivatives, but there's also a third derivative. Furthermore, Richard Nixon was the first sitting president known to have invoked the third derivative in a speech. He claimed that the rate of increase of inflation was decreasing. The rate of increase of inflation was decreasing. Now, inflation is already the rate of change of pricing. So inflation is the first derivative of prices. Inflation is increasing, the rate of change of the rate of change is increasing. So that's the second derivative. And then by noting that that is decreasing, he is dabbling in the third derivative. So I'll let you read that. But so here's the first derivative, second derivative, third derivative, and that's what it means in terms of pricing. Anyway, I hope that was helpful.